Hello, everyone. Welcome to the World Geothermal Congress 2020. I'm Ben Adams. I'm a professional mechanical engineer, and I'm going to talk to you today about work I did as a postdoc at ETH Zurich in the Geothermal Energy and Geofluids group. This work is on combining direct air capture and geothermal heat and electricity generation for net negative CO2 emissions. This work was in collaboration with Daniel Suter and Marco Mazzotti in the Institute of Process Engineering at ETH Zurich, and Martin Osar, head of the Geothermal Energy and Geofluids group, also at ETH Zurich. So in this work, we coupled direct air capture and sedimentary basin geothermal to find the CO2 captured for isolated and grid-connected systems. The geothermal system that we used in this work was a 2.5 kilometer deep, 50 millidarcy, 305 meter thick porous reservoir, the map view area of 1 square kilometer. The temperature of this geothermal reservoir was between 90 C and 140 C, which represent geologic temperature gradients of 30 C per kilometer to 50 C per kilometer, which are fairly typical geologic temperature gradients. It's nothing abnormal. So the reason that we couple these two together, and it can be advantageous, is because, first of all, geothermal heat and electricity is carbon neutral, or at least it can be, right? And it also you can provide both heat and electricity with geothermal energy. So geothermal energy tends to be a lower temperature resource than fossil generation, which means that the thermal efficiency tends to be lower for geothermal. So the efficiency in converting the heat to electricity is lower. So if you can use the heat directly instead of making electricity with it, it's to your advantage. And the DAC is energy intensive and also requires more thermal energy than it does electric energy. So for example, in the system that we modeled, 1,500 kilowatt thermal hours were required for 1 ton of CO2, whereas only 500 kilowatt electric hours were required for 1 ton of CO2. So we compared 4 systems. The 2 systems on the left, 1 and 3, those are grid connected systems. You see I drew a little green box around the grid connection there. And so that means that if any electricity, they would use the thermal resource completely, and then any electricity that was needed could be taken from the grid, presumably from another renewable source. And then the systems on the right, systems 2 and 4, are isolated systems, a power island. So there's no grid connection. So that means both the heat and electric loads for the DAC all come from the system itself, and there's no external energy source. And these are basically two different variations of the same system, one that has a parallel ORC and one that has serial ORCs, just 2 different ways we tried to increase the efficiency of the system. And all these systems have a geofluid stream coming out of the ground that's pumped, has a downhole pump to produce the fluid, the geofluid. And then the first half, there's a boiler, a heat exchanger that extracts thermal heat from the geofluid to vaporize atmospheric pressure water that's needed for the DAC. And then after that, the leftover heat then is used in an ORC. The system on the left here, top left, system 1, is the simplest DAC ORC combination that you can probably have with just one DAC and one ORC. We picked 105 Celsius as the center point here because we made the assumption that all the heat was needed within the DAC to vaporize water, and so it had to be at least 100 Celsius, and there's a 5 C minimum pinch on the heat exchanger as well. So for comparison, we had to just simulate the electric power generated for a conventional ORC geothermal system. So this is the power generated using our R600A isobutane ORC for different geofluid temperatures. That's on the x-axis here, from 90 to 140 Celsius, our variation produced geofluid temperature. And on the left is the power, the electric power, or electric or thermal power of the system. So you can see as as the temperature, resource temperature increases, your ORC makes more electricity. But also an important thing is on the right is our geofluid mass flow rate. So for each geothermal resource temperature, there is a flow rate that maximizes the electricity generated. Basically, at some point, if the cost to circulate the fluid faster and overcome the frictional losses of the system is actually costs more energy than it does electricity you can produce with that additional fluid circulation. So there's some flow rate that makes the maximum power, and that's what's plotted in the orange here for each geofluid resource temperature. So then that same mass flow rate is what we use in the when we couple the DAC and geothermal together. We use that same mass flow rate, so we're comparing at the same flow rate for all of our different systems. The thermal efficiency then increases with increasing temperature, so it's 2.5% at 90 Celsius and it's 4.5% at 140 C. So some results. For our first system, which is the simplest grid-connected system, combination of DAC and ORC, is shown here. On the x-axis is the temperature of our geothermal reservoir. On the y-axis is the CO2 that's captured by the system. And on the right y-axis is the electricity from the grid. We needed a minimum temperature of 105 Celsius to capture CO2, to vaporize the water for this simple system one. So for temperatures below 105, there's no CO2 capture. So the black line is flat at 0 below temperatures there. So because there's no CO2 capture, but you're still generating electricity with the ORC, it's actually, the electricity is negative here. It means it's actually going to the grid below 105 C. Then after 105, when the resource gets hotter than 105 C, you start capturing CO2 and using that electricity from the captured CO2. And at about 110 Celsius, then the system is balanced. That is, the electricity generated and the heat captured from the fluids, the geofluid, are just in the right proportion needed for the DAC. Then at temperatures above 110 C, then you see the electricity from the grid is positive. The orange line is positive. That means you need to have, in system one, you need to have electricity come into the system to capture the CO2. So you have a lot of thermal energy provided by the geofluid, but not a lot of electricity, so you need external electricity. Now system two. For system two, it's an isolated or a power island system. So the heat and electricity are created, all created with nothing external needed. So the orange line is flat at 0 in the whole way. In the system two, we added a heat pump so that at temperatures below 105 C, you could still capture CO2, basically by running a heat pump. And then at temperatures greater than 105 C, you're still just capturing CO2, although it's not as high as what was captured in system one, where you have external energy come in. And on the right, you see our electric power budget for system two. On the top, the positive electric powers. So if you look at 140 C, at the positive electric powers, that's what's generated by the ORC. And the system two has 2 ORCs in parallel. And so these 5.5 megawatts electricity is generated. And on the bottom, the DAC and the geofluid pumps have roughly the same electricity demand. And then the CO2 compression, which is also included to compress the CO2 captured up to 60 bar. that's included as well, but you can't see it because it is so small. Then all four of the systems kind of combine together here for different geothermal resource temperatures, different geofluid temperatures, to show you the CO2 captured for each. Below about the equilibrium temperature, 110, 109.5, is where the systems cross, where they're well balanced. The two systems that take electricity from the grid, system 1 and system 3, those increase much higher, and the power island systems 2 and 4, those increase less because there's less energy available to capture CO2, right? But this also shows that if you have, for some resource temperature, you could build a system so that you could take excess power from the grid, say from a variable generator like wind or solar, and you could use that when it's available. You could capture more CO2, and then if no excess power is available from the grid, you can operate just with the electricity you generate yourself, and you capture less CO2. You can capture less CO2. So it also shows how you could operate variably. How the operation could be variable depending on whether or not electricity is available from the grid. So also the system seemed to have was most efficient around 110 C when the electric and thermal loads were the best balanced. And you can see that here in this one metric we used called the electric opportunity cost, which is the geothermal electricity that would have been produced with the geothermal system plus any electricity you need from the outside per ton of CO2 captured. So it's the electricity that you gave up producing because you're capturing the CO2. And just that cost is the lowest, around 110 C. So our conclusions: we couple the direct air capture and sedimentary geothermal systems to find the CO2 captured for both isolated and grid-connected systems. And again, we use just a single 2.5 kilometer deep porous reservoir between 90 and 140 C. And so what we found is that about 40 kilotons CO2 per year could be generated with our power island system, the isolated system, or 180 kilotons per year when external power is allowed. And that these systems, in the way we configured it, operated most efficiently at about 110 C geofluid temperature, which is pretty low. It's only about 5 C greater than the outlet temperature from the DAC heat exchanger, which is pretty interesting that it works best at such a low temperature. And again, we did this because all the CO2 captured is all net negative. It's CO2 captured from atmospheric air, which is pretty unique. Thanks for listening. If you have any more questions, you can check out our paper in the WGC proceedings. Thanks for listening.